This week we've covered three main topics: strings and typography, images, and creating patterns. First, we looked at strings. There are a bunch of things that we can do with strings. The syntax is a little bit different than usual. Instead of providing the string as the argument to a function, we name the string, include a period, and then name the function. So for example, to find the length of a string, say it's called s, we would call s.length with an open and closed paren because it takes no arguments. And we get back the number of characters in the string. We can get pieces of the string by either calling char_at to get out a single character, or substring to get a range of characters from one index to the second. We can also search a string and find the first location of a substring. Finally, there are a bunch of little handy utilities. We can test to see if two strings are the same by calling equals. Remember, if you want to test to see if two strings, say s1 and s2, are the same, you don't want to type s1 == s2. That just doesn't work for strings. To test if two strings are the same, we want to call equals. And then there's some handy things. Trim removes the blank space at the beginning and end of a string. And of course, we can convert a string all to uppercase or all to lowercase. There are also a few other tools that we saw that we can do with strings. We can combine them. So here I have 5 separate strings, 3 words and 2 spaces, and I combine them all with the plus sign. The plus sign here doesn't add, instead it just puts 2 strings together. So the result here is I like bananas. Join does the same thing but for an array. So if we have an array of 3 strings and we say join, we give it the list and then we tell it what character to use to place between each of the strings. We get a result where all the strings are listed one after the other with the character we just supplied in between each one. The opposite of join is split. If we give split a string and we ask it to split on that string with a particular character, what we get back is an array of strings where each entry in the array is a single substring that is separated from the main body by that character. One of the great things you can do with strings is draw them up on the screen using text. And we saw the way to do that is a 3-step process. We load a font, we make the font active, and then we draw a particular string. Of course, this presumes that we use the font tool to create the VLW file for that font. So for example, we might load up the Courier font. We create a variable, here I'm calling it F, it's of type pfont or processing font. We call load font with the name of the VLW file that we created. Then we make this font active by calling text font and giving it the font object. Then we make the font active by calling text font and we give it the variable that holds the font we want to draw our characters in. Finally, now we're ready to draw a string. We just call text with the name of the string and the XY for where the string should be located. Typically, that XY is going to be at the left edge of the string and at the baseline, but we can control where the string is just like we can with almost any word processor. We can say that the XY we're providing is the left edge of the string, the center of the string, or the right side of the string. We can also do the same thing vertically. We can say that our XY is the top of the string, the baseline. It defines the center of the string, or the XY is at the bottom of the string. The default is left and baseline. If we want to do operations with the sizes of our strings, we saw that there are 3 measures that we can get out of any given string. We can find the distance from the baseline to the top of an ascender by calling text ascent. Remember, this is not exactly the same as the distance from the baseline to the top of a capital letter. And here, in fact, we can see that the lowercase f sticks up higher than the capital B. We can also find out how far most of the descenders go below the baseline by calling text descent. Both of these operations apply to an entire font. If we want to know how wide a particular string is, we call text width and we give it the string. And that tells us the width of that string in the currently active font. Moving our attention now to the second topic of pictures, we saw that we can load a picture from disk by calling load image. We give it the name of the file, and what comes back is an object of type pimage, or processing image. Now that we have a variable that holds a picture, we can draw it on the screen by calling image. It takes 3 arguments, the name of the picture, and the XY of the upper left corner. So for example, if this is our output window and we call image with the arguments picture 150, then at point 150, we locate the upper left corner of our picture. If the window is too small to hold the picture, whatever falls off the right and bottom just disappears. We can also talk to the individual pixels of a picture. Every pixel on the screen can be identified by its XY value. As always, X and Y begin in the upper left, X runs positive to the right, and Y runs positive going down. If we want to get back the color of the pixel on the screen at XY, we call get. If we want to set the color, say here to bright green, we call set, and that changes the color of that pixel. Get and set are bulletproof and a terrific set of routines to use, but they can be a little slow. If you need more speed, then you're going to want to use the pixels array. Remember, in order to make the pixels array hold the current pixels on the screen, you have to call load pixels first. From then on, you're just manipulating something in the computer memory. To actually see the results of any changes you make to the pixel array, you need to call update pixels. This can be very confusing if you forget, because you can spend a lot of time trying to figure out what's wrong with your program because you're changing all these pixels and you never see anything. Don't forget to call update pixels. The odd thing about the pixels array is that it's one-dimensional, and the screen is two-dimensional. So we have a little recipe for going back and forth between X, Y, and I, and back again. To find the value of I from a given X and Y, we use this little snippet of code. To go the other way, if you have a value of I, a particular entry in the pixels array, and you want to know what XY corresponds to, this little bit of code will compute X and Y for you. Speaking of X and Y's, we also saw an object called the PVector. A PVector is a type of object like any other, so here I'm declaring a variable named P of type PVector. It is just a single bundle that holds two things, X and Y. You can set the value of either of these two entries just by typing p.x and then assigning that to some value. You can also read the value out by typing p.x or p.y. This is really just a convenience, but it's a very nice one. Besides giving you a single place to store X and Y in a single variable, there are a bunch of nice built-in operations that work on p-vectors. You can set and get their values, and you can take two p-vectors and do the basic four operations, addition, subtraction, multiplication, and division of the two p-vectors. There's also a couple of handy distance operations, mag and dist, that tell you respectively the distance of the p-vector from the origin, 0, 0, or from another p-vector. So dist is a great way to find the distance between 2 points. Finally, there are a bunch of other operations, and all of these are handy if you get into doing geometry with p-vectors. Another great advantage of p-vectors is that you can make arrays out of them. So here we have an array of many different p-vectors. Each one is individually addressable. And we can even talk about the individual X and Y values just by naming the entry in the array and following it with .x or .y like any other p-vector. Finally, we talked about repeating patterns. Here's a pattern that goes between 0 and 1 over W seconds. So the question is, at any given instant of time, what is the value of this repeating pattern? Let's suppose that the variable t is a floating point number that holds the current frame count. Then we can find out the height of this pattern, which I'll call v, with just this little nugget of code. The quantity t mod w divided by w. That will go from 0 to 1 over w seconds, and then it will start again at 0 and rise to 1, and so on forever and ever. I showed you a set of 5 nice repeating patterns. First we looked at the sawtooth. It had this recipe. Remember that in this expression, both t and w are floats. Otherwise, your results won't be smooth and your animations will look chunky and weird. We looked at the square or rectangular wave. It had this recipe. We looked at noise, and that just meant creating a little array that held a bunch of values, and we stepped through the values of the array. To go back and forth, we use a triangle, and it has this recipe. Finally, if you want to go between two extremes but slow down at the ends and go a little faster in the middle, this sine curve is exactly what you want. It's easy to use. We just call sine, although remember to leave off the e, using an argument that's just the variable t times something. The bigger that number you're multiplying t by, the faster the sine wave will wiggle, the faster your motion will change. And then I almost always use map to convert the output of sine, which goes from -1 to 1, to the same range as all the others, 0 to 1. If you want this sine pattern to last for exactly W frames, here's the recipe for that. And that wraps up our survey of this week's topics: strings and text, images, and patterns.